Okay.
Yes.
Hopefully you can see my slides or our slides, sorry. So I'll start off. My name is Beena Ahmed, and with Vidhyasaharan, I'm in the School of Electrical Engineering and Telecommunications, and we work in the area of signal processing. So I'll start off, and then Vidya will take over from there. So I'm not going to give too many detailed results. I'll just give an overview of the different areas that I work with. So one area that I do a lot of work in is speech production assessment. So this is got applications in a number of areas. It is for screening of children with speech disorders, because currently around the world, there's around 12% of the population has a speech disorder of some sort. And over 70% around the world, children do not get diagnosed, let alone get treatment. In Australia, even itself, the numbers are bad. 50% of children in need do not get care. So once you've actually done screening, you can look at providing remote speech therapy for children and adults. So with adults, it becomes a case of a patient who's had perhaps a stroke, whose speech production has been impacted. They need rehabilitation. That's one example. Speech production assessment is also what I'm looking at is diagnosing of long-term degenerative conditions such as Alzheimer's, dementia, Parkinson's, ALS, and also mental health for depression detection. And then finally, this is not actually exactly a health application. It is but allow people with atypical speech to use assistive technology to allow them to use speech to control devices that can perhaps help them with healthcare. And so that's where I use speech production assess. And so in that context, what I'm trying to do is actually most of the work in speech recognition tends to focus on modeling the actual speech that has been produced and recognizing the words that have been said. My focus is looking more at the paralinguistic, the acoustics, and also modeling the articulators involved in speech production. The reason for that is when we model the articulators, we then don't need as much samples of disordered or atypical speech, because that's the biggest limiting factor in this work in this area is we don't have access to enough data to allow us to model all the speech problems. So I've given an example of some of the work we've done is we've actually to model the articulators. We model what are called the speech attributes, which actually specify the place and manner of articulation. This allows us to provide more formative input on why speech productions are not typical. Is there something wrong with the placement of the tongue? Is nasality an issue? All of that. These are all then linked to not just disorders that children might have, but also has impact. You can use these features we found to actually monitor dementia, Alzheimer's, and depression as well. And so some of these factors, we built a remote speech therapy monitor. This is a therapy system. This is for children. So we're actually assessing speech production, and we've gamified the speech therapy. And so the child is given remote feedback, basically automated feedback on how correct their production is. And the clinician can monitor this all remotely. And so this actually provides children who typically would not have access to care with speech therapy. So even in places like Australia, if we go to the rural parts of Australia, children don't have access to speech therapy at all. Even in major cities like Sydney and the outskirts, there are no speech pathologists. There's a huge shortage of this specialty in the world, let alone just in Australia. As I mentioned, we use it for dementia screening. That is because dementia impacts not just, it's not a memory thing that the words that you're using, it's also actually your speech production. And we actually did some studies that found if you have speech which is cognitively, where you put some cognitive load on the patient that highlights some of these features that differentiate between typical and people with who are pre-dementia. You can identify it. And so we were able to actually identify markers that can be used in a screening tool for dementia. And over here, I've shown some examples of, over here, we have a sample from, this is a healthy patient at the top. And this is, and here sorry, at the bottom we have, I meant to say, bottom is a healthy. As you can see, the words are much shorter. The gaps are much shorter also, whereas on top where we have low cognitive reserve, the patient is taking much longer to say these samples. However, it's not as clear as simply putting those features. The systems that we've built are actually quite complex, that they use some of these inputs. And so that's why a lot of my work has been recently on trying to actually disentangle representations of speech that can be used to track different conditions. I mean, we know speech contains information about our identity. We know speech contains information about what we are saying. What we need now to isolate is information about our well-being. So whether that's cognitive decline, mental health, speech disorders. So a lot of my work recently has focused on trying to identify this, how to actually disentangle these representations. This was where I had spoken about assistive technology. So this is more of a societal impact application that I've been working on is in the global South, especially when it comes to maternal health. A lot of women do not have access to healthcare. And when they do have access to healthcare, it's quite patchy. So in other words, they'll go to one healthcare center once and 3 months later go to another, and they will not have any health records with them to take forth. No papers, no documentation. So you'll have cases of women perhaps who have hypertension during pregnancy, have been told to take medication, but not realize the seriousness of it. And when they go to the next time, they don't have any records of their previous diet. And then, obviously, this can have negative impacts both on the mother and the child. So what we've done is we create a system where a clinician can dictate voice notes, which we are converted to text, and then we then use language models to generate full-fledged electronic health records for the patients, which the patients can then keep on their own devices, and they can then take to wherever they go next time for their health checkup. So this allows continuity of care. It also allows flagging of health concerns. So for example, as I told you, the example of the hypertension. So if the health check flagged something, that would be flagged. Conscious of time. And then we've also created a local system for the patient themselves where they can enter information. So it's like a assistant for them. And then also we've looked at using LLMs with signals collected remotely from the patients. One example I have over here is sleep monitoring. This is to diagnose sleep disorders. So we've actually looked at how to tokenize the signal so that it can be inputted into the LLM, which can then do the disorder classification. We've also done something similar with ECG as well. Okay, and in interest of time, I'll stop there and pass to Vidya. Thank you.
Thanks, Beena. So I'll continue on to talk about some of the other things that we're doing that kind of underpin all of these applications. So one of the problems we've been working on is actually the problem that Sriram spoke about on quantifying uncertainty and confidence in predictions. So one of the things that we've been working on for the last few years is this problem of uncertainty can arise from many different sources, right? You can have model uncertainty, you can have uncertainty arising from data, uncertainty arising from distributions, aleatoric and epistemic uncertainty. And we've been working on methods, techniques to quantify the total uncertainty as well as to distinguish between the different types of uncertainty, like sampling from the model space and sampling from the distribution space and things like that, which then leads us to, Beena, if you go to the next slide, to a significant problem in a lot of AI spaces, which is to deal with domain adaptation or distribution shifts. Models are trained on data from particular domains, but then they don't generalize well to similar data from a different domain, like, for example, in a different setting with different equipment and so on and so forth. So we are working on techniques to sort of introduce domain shift, domain alignment into the data. So either move the model or move the data. And a lot of the focus has been on actually moving the model to where the target data has been, because it can be in many different places. And here again, we leverage the previous work on uncertainty, with the idea being, if there is domain shift, there'll be greater uncertainty in making prediction. And then the way to correct that would be to modify the model so as to reduce this uncertainty. We're also looking at local geometric structure of the data, trying to preserve that while we do the domain alignment. And the next one, Beena. Maybe the last thing I'll mention is a related but somewhat different topic, which is uncertainty or ambiguity in the labels. Again, when you're dealing with problems like emotions and mental state and anything that's subjective, ground truth is hard to pin down, because you could have different opinions, different perceptions of the same thing. So it requires a class of machine learning techniques and models that can deal with the labels being ambiguous, right? And again, this is we've got about a decade of work going back on developing systems that can deal with ambiguous labels, and especially ambiguous labels that evolve with time. So what happens? How do these quantities evolve with time when you only have ambiguous labels about what's happening? So I'll stop there, and then we can discuss further towards the end. Thank you.
Thank you.